Recording.
Okay, the second talk of this afternoon will give by Professor Manuel Gonzales Burgos, or Manolo Burgos, if you prefer, from the University of Sevilla. And the title of his talk is Controllability of Parabolic Problems with Distributed Control Supported on a Hyperplane. Okay, Professor.
Thank you very much, Marcelo, and thank you, the organizer, for inviting me to this fantastic event. Well, the general objective of this talk is to revisit the moment method and to provide new controllability results for the heat equation, but in a framework, in the n-dimensional framework. And to this end, I'm going to present a new result, and which is the heat equation, but with a distributed control, which is supported on a hyperplane. And this is more or less the contents of my talk. Well, let's start with the first point. And to this end, I'm going to show you the problem under consideration. And to this end, we are going to fix n, a positive integer greater than or equal to 2, and omega, which is a cylinder, is the cylinder omega 1 times 0 pi, with omega 1 a regular bounded domain in or n minus 1. We are going to follow this notation. The point of or n will be denoted by x prime in omega 1 and x in 0 pi. And on the other hand, we are going to fix an little omega, which is an arbitrary non-empty open set, and a point x0 in 0 pi. And a positive time. With this element, we pose the problem, the following null controllability problem. Given initial datum y0 in L2, we want to find a control V in L2 of little omega times 0t, such that the solution of this problem 1, which is the heat equation with a right-hand side, y equal to 0 on the boundary of the domain omega, and the initial datum y at time t equal to 0 equal to y0. And we want to control a control find V such that the corresponding solution at time t is equal to 0. The right-hand side is the control. The control only depends on x prime and t, but the control does not depend on x, on the last variable x. And in fact, the x is fixed because we have here the Dirac delta on the point x equal to x0. This is the situation, the geometrical situation. We have a cylinder, omega equal to omega 1 times 0 pi. The control is supported in little omega, but the control only acts on the hyperplane x equal to x0. And we want to control with such control V in such a way that the solution at time t is equal to 0. And this is our null controllability problem. Well, this problem is very well known in the one-dimensional case, when n is equal to 1. In this case, the problem is the following: is this problem 2, the heat equation in dimension 1. We have in this case a control V which only depends on time, and we have also the Dirac delta at point x equal to x0. Then we have a control only on the point x0. And this control depends on t. Well, this problem is very well known. The solution of this problem is very well known. This problem was studied by Dolepki, and he proved that we have, in order to have the null controllability result, we have to add a necessary condition. x0 must satisfy this condition. X0 over pi must be an irrational number. And this condition is equivalent to the approximate controllability of this problem. Now the question is the null controllability of this problem. We have to assume, of course, that x0 over pi is an irrational number, and here we have a minimal time. We have this quantity, t of x0, which is defined by this limit soup. This quantity is a quantity between 0 and infinity, and we can prove that if t of x0 is a number and t is greater than this quantity, t of x0, then the system is null controllable in L2 of 0 pi. On the other hand, if t is positive, t of x0, sorry, is positive, and t is less than t of x0, in this case, the null controllability, the problem is not null controllable at time t. We have in this case a minimal time, and the the problem is not controllable if t is less than this minimal time, t of x0. Well, we know also some result in the case n greater than or equal to 2. In this case, it's a result by Lat-G-Sam. And, well, the first thing is that we have, again, the same necessary condition. x0 over pi must be an irrational number, and this condition is, again, in this framework, in this n-dimensional framework, is equivalent to the approximate controllability. On the other hand, we have the same time, the same minimal time, t of x0, which is given by this limit soup, and we know two results. The first one is the case in which omega is equal to omega 1. We have a global control, supports this on my hyperplane by global. In this case, we can obtain the same result that the same result as in dimension 1. In the other case, the general case, the case in which omega is a part of omega 1, omega is different from omega 1, and only in the case of in which x0 over pi is an algebraic number of over 2 or greater, in this case, the minimal time is equal to 0. Well, in this case, Lat-G-Sam proved the null controllability result for this system at any time positive t, any positive time t. And the other cases remain open. Then, in our case, this is our objective, to prove the null controllability of 1 in the general case in which omega 1 is a part of omega. And to this end, we are going to apply the moment method, because we have some elements for applying this method. The main tool is to know the eigenvalue and the eigenvector of the Dirichlet-Laplanche operator on omega. Omega is omega 1 times 0 pi. And in this case, the eigenvalues are given by mu m plus k squared, and the eigenfunction, normalized eigenfunction, are given by this product, Cm x prime sine the sinus of kx. And in this case, mu m is the sequence of eigenvalues associated to the associated to the Dirichlet-Laplace operator, but in omega 1. And Cn are the corresponding sequence of normalized eigenfunction. Well, with this element, it is possible to solve explicitly the problem 1. For any y0 and any v, we have a formula for the corresponding solution y. We want to obtain that a control v such that y at time t is equal to 0, and this gives directly this problem, the moment problem. There exists a control v such that the solution at time t is equal to 0 if and only if v satisfies this infinite number of equations. Well, the scalar product in L2 of little omega times 0t the scalar product of these quantities, this exponential times Cm V, is equal to one quantity on the right-hand side, where y0 mk is the coefficient, the Fourier coefficient of the initial datum. Observe that in our case, the sinus of x0 is different from 0. If you want to obtain a solution, this is necessary. If not, the problem has no solution. And this is the assumption. X0 must satisfy that this sinus is different from 0, and this is equivalent to this property. X0 over pi must be an irrational number. Then this is our moment problem, and this is equivalent to the null controllability at time t. We want to find a control V which depends only on x prime and t, is independent on x, the last variable, such that this scalar product, this function, the scalar product of this function and V is equal to some quantities n, capital N, and K. And in this case, this quantity mk is equal to this formula, the exponential, a negative exponential with the eigenvalues 1 over the sinus times the Fourier coefficient. Then we have an infinite number of equations, and we want to solve an infinite number of equations with a control V. Okay. This in particular, these quantities, this function, the exponential times Ci, must verify some property. If not, the problem is not compatible. And, well, in some way, this exponential must be minimal, linearly independent. And this is equivalent to find a bi-orthogonal family. And this is the definition. Let's take fmk equal to this exponential times Cm, psi m. Then we say that qmk is a bi-orthogonal family in L2 of omega times 0t of fmk, if this quantity, this scalar product fmk, the scalar product in L2 of omega 0t of fmk qnl is equal to 1, if n is equal to n and k is equal to l, and 0 otherwise.
William?
Juan?
I can't hear Manolo. We can hear you.
Your
At least
audio?
I can. Now, Manolo?
I had a problem.
Yeah.
Well, I don't know. You see my slide? No,
No.
sorry. Compartir. You see my slides?
Yes.
Okay. Sorry.
Okay, no problem.
Then, well, summarizing, we have a null controllability problem. This null controllability problem is equivalent to a moment problem. And with this concept, like the concept of bi-orthogonal family, we have a solution. The solution V is equal to this quantity, and this quantity solves our moment problem. Then the question is, it is possible to prove the existence of a bi-orthogonal family to this fmk in L2 of little omega? And if the answer is yes, we can prove the convergence of this control, because this control must live in L2 of little omega. Then this series must be convergent in L2 of omega times 0t. Well, the answer is yes in both cases, and we can prove this result, which is the main result. Well, the main result reads as follows: there exists a constancy such that for any positive t, the sequence fmk admits a bi-orthogonal family qmk in L2 of omega times 0t. And in fact, we can bound the norm of qmq in L2 of little omega times 0t. And this norm is less than, well, the constancy, the exponential of c over t, and this exponential of c square root of the eigenvalues mu n plus k squared. Well, with this theorem, we can prove the null controllability results. Well, I remind you that we had a point x0, which is an irrational, x0 over pi is an irrational number. We had a candidate for solving our problem, and v, and the coefficient m and k are given by this quantity, and the norm of q and k is not too large. Is less than or equal to this quantity here. Then now the question, is this series, convergent in L2 of little omega? Yes, the answer is yes if t is large enough, because we have here the exponential of c square root of mu n plus k squared. This is not a bad quantity. We have an exponential of minus the eigenvalues sine t. This is fantastic, but we have here 1 over the sinus of kx0, and this quantity could be very, very small, in such a way that 1 over the sinus must be very large. Then t must be large enough in order to absorb in some way this quantity and to prove the the convergence of V. But this is possible in the case, and this is, well, we can prove this theorem. This is possible. The previous series is convergent if t is greater than t of x0. Then we can prove that the null controllability result if t is greater than this minimal time, t of x0, and for t less than t of x0, we know that the system is not null controllable even if little omega is equal to capital omega 1. Then this is
Again, Manolo.
Problems again.
Well, I think I have a problem with my connection, and well, we restart.
Okay. Oh, if you connect via mobile data,
No,
I don't know.
no, I prefer to continue
Okay.
with
Okay.
yeah.
Wi-Fi. Okay.
Control L. Okay, okay. Then summarizing, we have a omega 1 bounded domain with boundary regular enough. We have mu m, the sequence of eigenvalue, and cm, the sequence of normalized eigenfunction in L2 of our operator, which is the Dirichlet's Laplace operator in omega 1. We had f and k equal to this quantity, and the objective is to prove the existence of a B-orthogonal family which satisfies this additional condition. The norm of q and k must be bounded. And here the main difficulty comes from this fact. Omega is different from omega 1. Then this is the objective, to prove this result. And to this end, we are going to follow 3 steps. The first one is the gauge in which little omega is equal to capital omega 1. In this case, observe that in this case, Cm is an orthonormal basis of L2. And then, well, we can prove the existence of a B-orthogonal family in L2 of omega 1 times 0t. The second step is the main argument. We are going to prove that this operator, the restriction operator, the operator which is defined by R omega of psi is psi restricted to O little omega, this operator is inversible, is a bicontinuous bijection between the closest space of L2 of rho omega 1 times 0t spanned by the f and k. Rho is a weight, is an appropriate weight, and is a bijection with values in the space spanned by f and k in L2 of little omega. We are going to prove that this restriction operator is a bijection, bicontinuous bijection between these 2 spaces. Finally, using this property for the restriction operator and using a B-orthogonal family in L2 of omega 1 times 0t, we can prove the existence of a B-orthogonal family in L2 of little omega times 0t. Well, I prefer don't go into detail, but in any case, I'm going to give you some ideas of the proof. Then we are going to prove the first step. We are going to prove the existence of a bi-orthogonal family in L2 of omega 1 times 0t. And in this case, this is the result we can prove. There exists a constant C1 such that for any t and for any epsilon between 0 and t over 4, there exists a sequence only depending on time, qmk epsilon, only depending on time, such that the function fmk epsilon, which is equal to qmkt times cm of x prime, this family is B-orthogonal to fmk in L2 of the capital omega 1. And in fact, we can prove that this fmk epsilon is 0 between 0 and epsilon, for t between 0 and epsilon. And the norm of this quantity is not too bad, because it's a constant, an exponential over t times the exponential of C1, the square root of the eigenvalue mu n plus k squared, and we have another quantity you can forget. This is the proposition. And this proposition is not too difficult to be proved. First, we work with the sequence lambda k equal to k squared. We know that the exponential of minus k squared t admits a B-orthogonal family. This B-orthogonal family, qk, is bounded in a very convenient way. Now, we fix the sequence mu m plus k squared, but m is fixed. Then, in this case, for this new sequence, mu m plus k squared, this exponential admits also a B-orthogonal family, which, in this sense, the integral between 0 and t, this exponential time qm ml epsilon of t is equal to delta kl. M here is fixed. Well, we can prove this, a kind of uniformity property, because here the constant is independent of mu m. And now it is very easy to prove that using that Cm is an orthonormal basis of the L2, it's very easy to prove that this QMK epsilon times Cm is a orthogonal family in the 4FMK. Then the proof is not too complicated. Then what happens if now we want to work in little omega? Well, if we work in little omega, Cm is not longer an orthonormal basis in L2 of little omega. We lose the orthogonality property if we work in L2 of little omega. In some way, we have to measure this loss of orthogonality. And to measure, in some way, to measure this, we are going to measure this loss using. Okay, sorry. First, observe that this result, the system of a orthogonal family, permits the proof, the null controllability, when the control acts on when V is a global control. The support of V is in the hyperplane x equal to x0, but with respect to x prime, the support of V is equal to omega 1. We have a global control, and we can prove the null controllability in this case. Okay, as said before, we have to measure in some way the loss of the orthogonality when we work in L2 of little omega. And this is the part of, to do this, we are going to use the spectral inequality. We know the following result. Fix omega 1, a bounded domain regular enough, omega a little open set of omega 1. Then there is a constant beta positive such that for any sequence Cm and for any lambda between 1 and infinity, the norm of this finite combination of Cm, the norm in L2 of little omega, is bounded by the norm of this quantity in L2 of little omega times a constant. And this constant is the exponential of beta lambda. This is the way of measuring the loss of the orthogonality property. For a proof, this result was proved by Jerison and Lebeau, and it's very classical. Where we are going to use this property, and we are going to apply this property to this combination, finite combination of FMK. We take a combination, a finite combination, the FMK. This is this quantity, the Km times the exponential, the negative exponential, say m, and we can prove this theorem. There is a constant alpha 0 and a time t0, only depending on beta, such that we have this inequality. The norm of this combination, finite combination, the norm in L2 of omega 1 times 0t with this weight, this exponential, negative exponential, alpha beta over t, this quantity is bounded by 6 times the integral of Pm, but in little omega times 0t. Then the restriction of Pm, the norm of Pm in L2 of omega 1 times 0t is bounded by the restriction of Pm to little omega. And this is true for any t less than or equal to 2 tau 0, and for any alpha, and for any m, and for any Pm. Well, this is in some way the restriction is inversible. This inequality says that we can inverse in some way the restriction when we work with this function f and k. Well, this is the crucial theorem and the most difficult to be proved. And some ideas. The idea is to apply the spectral inequality to PM. PM is this sum and is in particular this coefficient GMMT find CM. We take CM equal to GMMT. We apply the spectral inequality and we play with time. And, well, we use the dissipation on the interval alpha 0 alpha over m and alpha m over t. Well, and after some computation, we can prove this theorem. I prefer don't go into detail, but in any case, well, this is the conclusion. We have proved this theorem. Okay. In particular, we are going to take this quantity and alpha of x prime, which is equal to 0 if x prime belongs to omega and alpha beta else otherwise. We are going to work with this L2 Hilbert space with weight. The weight is given by this exponential minus n alpha x prime over t. Okay, we work also with this closed subspace E eta alpha, which is the span of the family FMK with norm in L2 of n alpha and A, which is this quantity, this closed space. Then, from this result, from the previous result, we can prove this result. If t is less than or equal to 2, 0, and alpha is greater than or equal to alpha 0, in this case, R omega satisfies these inequalities. The norm of phi in the space L2 of eta alpha is less than or equal to 7 times the restriction of phi in L2 of little omega. At the same time, is less or equal to 7 times phi in L2 of the L2 at eta alpha. And in fact, R omega, this restriction operator, is an isomorphism between these spaces. Okay, the result is very technical, but in any way, this result give us the solution. Okay, the conclusion is then that we can prove our main result. This is our main result. The S is of AB orthogonal family, and this in L2 of little omega. This is important, and the norm is bounded in a very, very nice way. And the proof combine first the S system of AB orthogonal family in L2 of omega 1, and second, the second point is the restriction operator. It's an isomorphism, then we can construct AB orthogonal family in L2 of little omega from the AB orthogonal family in L2 of big omega 1, capital omega 1. And this is the result, and this ends in some way the proof. Well, in order to finish, some generalizations. Well, we have worked with lambda k equal to k squared. Well, in fact, we can work with any sequence of eigenvalue associated to an elliptic operator in dimension 1. The operator L given by this equality. The second remark is that lambda k could be complex. We can prove the same result with general complex sequences which satisfy some condition. The first condition is the real part is positive because it's an elliptic problem. The imaginary part is not too large, it's less than or equal to beta, the square root of the real part of lambda k. We have this condition, this is the counting function, this in some way measures the behavior of our sequence. This says that the sequence lambda k, the modulus of lambda k is more or less k squared. This is this condition. And the third one, we have to add some separation, some gap condition for our complex sequence. In this case, we have to verify that lambda k minus lambda n is greater than or equal to this quantity, rho k squared minus n squared. This for when k and n are large enough, separated, and this infimum is positive. Well, in this case, we can prove the same result. But in fact, we can even eliminate this third condition, because in this case, the infimum could be 0. This means that the eigenvalue could approach. Or if you want, we can have condensation of the eigenvalue. In this case, we can prove the same result. The proof is much more complicated, but we can prove. And well, this is all. Thank you for your attention. Obrigado.
Okay. Thank you, Manolo. Very nice talk. To the audience, do you have any questions, comments to Manolo? Juan, can you see any hands?
I have one question, Manolo.
Okay.
Hello.
Hello.
The hypothesis that you assumed in the first results that x0 over pi does not have to be rational. Yes, it's because it appears sign dividing, no? At some moment, no? There is
Sorry.
the reason why you suppose that is because it appears a sign function dividing.
Okay, so this comes from the sinus of kx0, which must be different from 0.
That's the main reason, no? Yes.
For any k. Yes. Yes.
Okay. So thank you. I like to hear you. Thank you, Manolo.
Okay, do you have any other questions, Manolo? So if no, let's thank the speaker. Thank you, Manuel.
Thank you very much for your attention.